Here is the next example. In this example, he's asking about draw the input and output waveform and transfer characteristics for the given circuit. Assume the constant voltage drop model. Okay, this is the given circuit. So as I mentioned, we always start with assuming one diode is closed, another diode is open. So here I'm assuming D1 is open and D2 is closed in the sense there is a 0.7 voltage drop because of the constant voltage drop model. Or assume the practical diode. Practical diode is also nothing but you will end up having 0.7 volts voltage drop. Now my current I equal to I found the current passing through the circuit. Since this is open and everything else look like a DC circuit, apply KVL, which is 10 minus 0.7 minus 2 volts divided by 5k plus 5k, which is 10k. So I found the current has 0.73 milliampere. That is the current passing through this circuit when diode D1 is open, D2 is closed. Now once I find our goal is finding V0. So 10 minus V0 must be equal to 5k times I. 10 minus V0 equal to 5k times I, end up with V0 equal to 6.35 volts. So the output voltage I found here. Now I need to find the condition. What condition? What input, at what input voltage I'll get this output. Okay. So here I assume this diode D1 is open, right? So based on that, I wrote this equation. I assumed that diode is open, so V0, anode voltage here, must be V0 minus Vin must be less than 0.7. Okay, so now I'm going to substitute V0 value here, which is 6.35 minus 0.7 must be less than Vn. So if I substitute that, it is 5.65 must be less than Vn. So as long as Vn is greater than 5.65, as long as, so from this, if Vn is greater than 5.65, then my output is going to be clipped at 6.35 volts. So that's the condition I found from assuming D1 is open, D2 is closed. So I'm going to come up with the second case. In the second case, I'm assuming this D1 is closed. Closed means constant voltage drop model. D2 is open. Okay. So from this, V0 minus Vn must be equal to 0.7 volts. So V0 equal to 0.7 plus Vn. So I found the output voltage, but I need to come up with the equation. So the equation is, I'm assuming D2 is open, right? So V0 minus, since D2 is open, there is no current passing through this 5k ohms, so that is 0 ampere. So voltage at that point must be 2 volts. So V0 minus 2 must be less than 0.7 volts. So I'm going to substitute V0 value here. So 0.7 plus Vn minus 2 less than 0.7. We'll end up with the Vn is less than 2 volts. So if Vn is less than 2 volts, then V0 equal to 0.7 plus Vn. So from the first case, I end up so I'm going to take the sinusoidal waveform here. Let me draw this. So here is the sinusoidal waveform. So I found if Vn is greater than 5.65 somewhere there, I know what is output. Here, if Vn is less than 2 volts, so less than 2 volts somewhere here, I know the output right there. So I need to find what is going on during this period. So the third case, I'm going to assume both diodes are closed. Why not both diodes are open? If I assume both diodes are open, you can clearly see the given circuit. If both diodes are open here, if both diodes are open here, then the voltage here is going to be 10 volt. You're saying anode voltage is 10 volts, cathode voltage is 2 volts. For sure, D2 is going to be closed no matter what. So That is the reason I'm not assuming both diodes are open. So third case, I assumed both diodes are closed. So I found that V0, so based on this, here is my V0. V0 minus Vn must be 0.7 volts. That's the same equation we used in the previous case. So V0 must be 0.7 plus Vn. So I found the V0 value. Now I need to find the condition. What condition? I get this V0. So here the current passing through D2, I'm taking that as I2. I2 must be greater than 0. So V0 minus 0.7 minus 2 divided by 5k must be greater than 0. So V0 must be greater than 2.7 volts. So I'm going to substitute V0, this V0 right here, which is 0.7 plus Vn must be greater than 2.7 volts. So as long as Vn is greater than 2 volts, then V0 equal to this. Okay. So from this triangle, from this sinusoidal waveform, that's 2 volts. I know what is going on above it, but at the same time, we need to find the upper limit. So to find the upper limit, what I did, I took the current I1. So I current is starting from this 10 volt source. It's going to split I1 and I2. So I use the KCL at that junction. Now I'm assuming I1 must be greater than 0 since that is acting like a closed switch. So I1, I don't know how to find I1. So I used the KCL. And based on this, I can write it as I1 is nothing but I minus I2. I can write for I can write for I2. I is 10 minus V0 divided by 5k. 10 minus V0 divided by 5k will give me I. And I2, we just wrote down this equation. This is I2. Okay. V0 minus 2.7 divided by 5k must be greater than 0. So once I solve this equation, I end up with 12.7 must be greater than 2V0 and 12.7 divided by 2 must be greater than V0, 6.35 must be greater than V0. Now substitute V0 value into Vn. So substitute this value right there. End up with as long as Vn is less than 5.65, I will end up with that value. So those are the three conditions we end up with. So from these three statements, you can clearly see if Vn is greater than 5.65, my output is going to be clipped. If Vn is less than 2, output is going to be this much. If Vn is between 2 and 5.65, that's the output. Now I'm going to draw the waveforms. So here is the sinusoidal input waveform. That's omega t. Here is my Vn. So here is my output. Now you can clearly see my input is 0. So here is my input between, so actually right here. So if Vn is less than 2, V0 equal to 0.7 plus Vn. So if Vn equal to 0, my output is equal to 0.7. So my output is going to start at 0.7. So follow the input. When it reaches, my input reaches to 5.65, my output is going to be clipped at 6.35. So this is 6.35. You need to indicate all these values in the waveform to get the full credit. And this must be 5.65 volts. Okay, and the rest of the cycle, so below 2, this is my output, and even between 2 and 5.65, that's my output. So it's going to be look like something like this. Okay, so here this must be at 0.7. This must be at 0.7, must be at 0.7. Okay. must be 8.7, must be 8.7. This must be right there. It's a good idea to draw this dotted line so you can see exactly where it is clipped. Now from this I'm going to draw the transfer characteristics. So my input is varying +10 to -10. So here is my input, a dotted line. Now my output is going to start at, it's not 0.5, it is 0.7. My output is going to start at 0.7. Output is going to start at 0.7 and it goes up to 6.35. So that is 6.35. At that point my input is 5.65 volt, and then reverse side it is going to be constant. So here we'll reach -9.3 volts. So in the waveform also it's a good idea to indicate -9.3 volts. How did I get this -9.3? So you can see if the input value is less than 2 volts. So less than 2 volts means -0, -1, -2, -3, -4, -10. So if my input value is 10 volts, what is my output? I mean -10 volts. If the input value is -10, what is my output? -9.3. That's how I end up with the -9.3. Okay, and it is going to be constant at this point. So this red line is the transfer characteristics. So the red line is the transfer characteristics. I'll stop this video here. If possible, I'll solve a couple of more examples. Thank you.